Welcome to the pre-recording of lecture 5 of MCS 481. In this lecture we consider the problem of overlaying subdivisions. So this lecture follows the line segment intersection problem. We will apply essentially the line segment intersection problem, and also follows the previous lecture on the overlay of maps. As much as possible, this lecture will be self-contained. I will start by re-explaining with examples the doubly connected edge lists. These are used to represent the subdivisions that we will be overlaying. So the line intersegment problem is a very important problem in computational geometry. Think about a map with rivers or railroads and a map of roads for vehicles, and you would like to know the intersection of these two, the overlay of both maps. So we will explain how this computation of the overlay of subdivisions is also an output sensitive algorithm. It will depend on the size of the output. So it will be an extra extension of what we have covered in the last lecture when we considered the line intersection problem. Now there is an extra term, which is the output will also contain the information of the faces. Okay, so let's go back to doubly connected edge lists. So when we talked about convex hulls, we were talking about counterclockwise and clockwise orientations. Let's look at a planar subdivision. So here is an example. We have a square inside a pentagon. So this is in the plane, but we have objects of 3 different dimensions. A vertex is 0-dimensional, an edge or a line segments connecting vertices is 1-dimensional, and then we have the 2-dimensional pieces. So the pentagon separates the inside and the outside. The pentagon, if you like, has a square hole in it, so this is another face. So we have 5 vertices and 5 edges from the pentagon, 4 edges and 4 vertices of the square hole, and then we have the 3 faces, what is outside the pentagon, and then the pentagon itself, and then the hole inside the pentagon. So we have seen Euler's formula, the number of faces minus the number of edges plus the number of vertices is larger than or equal than 2. So this is a disconnected graph. If the graph would be connected, if you have one more edge here, then actually you would have that the Euler's formula might actually be the inequality might be turning into an equality. Okay, how do we represent this? So that is the key now. Well, we defined vertex records, edge records, and face records. Here is a representation, here is an example, a recall of a vertex record. So the vertex in consideration is this V here, so that's what we consider. So this is the vertex V. So what we store, I'm sorry, what we consider is actually an edge, I'm sorry. So an edge is that what we consider. V is the origin, so that's the first item that we store. Every edge has a twin, so the origin of the twin is actually the destination. So that's why the destination of the edge, so typically a line segment, so you would have a beginning and an end. Here actually we store the origin and the twin. Then we have a previous and a next, and then there is the incident phase. So the incident phase is the phase that is actually enclosed by the counterclockwise walk around the edges. So actually you have the in the direction of the walk, the face that is enclosed by the edges is always to the left. That's important to keep in mind. Okay, here is how we represent, or at least the picture here has the focus on the edges, on the doubly connected edge lists representations. So you see what I just said, the counterclockwise. So the counterclockwise here, the incident face is the hole, the square hole. We have what is inside the pentagon, the counterclockwise there. So that is the incident face. So for every face we have the inner components and then the outer. So that was defined as well in the previous lecture. Okay, what is now the problem statement that we consider specific in this lecture? So we consider, and it will boil down to an application of the line intersection problem, a problem we can solve already. Consider two doubly connected edge lists. They represent two subdivisions. So we have in the red our beginning pentagon with a hole, with a square hole. And then we overlay, it with the green triangle. So at the right, so the green combined with the red gives the blue. So you see what this results in is more edges, not more edges, but there will be more edges because we will split the edges. We will split both green and red edges, but where we split them are the intersections of the line segments. So there you can see the importance of the line segment intersection problem. So at this point, it's very good to pause a little bit, and if this is a pre-recording, you could pause at the this moment now. So you see on top we have the doubly connected edge list for the pentagon with the square hole. You should take that picture and modify it so that and you can also actually draw the doubly connected edge list for the triangle. And then you see that the intersection will create not only more vertices, but also more faces. So the rule is that every doubly connected edge list, you have the counterclockwise orientation for the incident face. So here you have this new triangle. So if you go to the new triangle, so you have this property that needs to be maintained. If you look at the new face that is created here, the edges need to be oriented so that the counterclockwise orientation follows the inside of this face here of what we call the incident face to the um, doubly connected edge list, or the incident face to this edge list, the edge list that is oriented counterwise. So we have these cycles that are defined by the planar subdivision of the output. Okay, so that's the first exercise. So it's actually important that this exercise is done because then you get a kind of a feeling of what is the output of this particular example. All right, then here is the first version of the map overlay algorithm. We have given two doubly connected edge lists, and then the overlay will be stored as another doubly connected edge lists. And you see the second step in this algorithm will be the sweep. So what we do in the first step, we collect all the line segments. So in some sense, let this fancy D be the edge lists. It's actually the lists of all the line segments that appear in the subdivision. So we extract all the line segments from there. So we compute, applying the line sweep algorithm, we compute all the intersection points. And then for every intersection point, we will have to compute new half edges and do the connections with the previous and next for the existing edges. And then we use the edge lists to also to update the faces. So this is the general outline, the first outline of the map overlay algorithm. So you can see that this will have already the same cost as a lower bound as the line sweep algorithm that we applied for the line segment intersection problem. So the cost of step 2 is proportional to n plus the size of the intersections times the logarithm of the number of line segments. So how do we now compute the new half edges? So there is the case where there is already a vertex. So we have to compute. So this intersection point here. So we have already the red, and then we need to compute. We don't need to worry about. So we have this intersection point P that actually will be used to split. So the edges will be shortened, and the shortened edges will have new half edges as the twins. So then we need to set the origin right. So this is the case where the new intersection point is already a vertex of the first subdivision. Okay, then the connection of the pointers next and previous. So what we do is every shortened edge, we change the orientation. So what is actually happening that for every edge, what we have, actually, I'm actually a little bit, so there is the counterclockwise orientation that needs to be preserved. So what we have is that the orientation of the red edges needs to be consistent with the orientation of the green edges. So that is actually the point. So we have the next. So if we have shortened the edge, the original edge, so it actually has its next change to the first counterclockwise edge. So that is the point that I want to make. So the next of this green edge would be another green edge. But actually it should be the next here should be the properly connected with a red edge. So we have the old half edges that actually play a role. So we have to set the origins right, but then the new half edges, they have to copy their next from the old half edges. So the picture actually makes things a lot clearer than the text, what needs to happen. Although from the pictures you can't really see what is the next of the green edge. So this should be this red edge here. The same here, the previous should not be the previous green edge, but it should be an old red edge. Okay, let's transition to the faces. But the point of this exercise here is that we have the new intersection points. So this exercise 2 follows exercise 1, and it's actually intended to better understand the previous slide. You see, in preparation for this pre-recording, I did not solve the exercise myself. I solved it once, but in preparation for the pre-recording, I didn't do this. So I blanked out a little bit on the previous slide. The purpose of this exercise is that if you make it properly, and of course you need to do first the first exercise, is you do this second exercise, then you will comprehend the rules on the previous slide. So that is also the goal here. Describe in sufficient detail what is happening in the setting of the next and the previous pointers. Okay, so you can pick any of the new yellow points. So you can pick this point here, and from your previous exercise you can describe that this edge was splitted, so the green edge here was splitted, but then actually also we splitted the red edge. So what was explained, and that's also actually the purpose of this exercise, this is explaining what happens if you need to split an edge of both overlays. All right, so now let's move on to updating the face records. So we have to updating the after the computation, after splitting the edges, we have to determine the face record. So we have new faces, but so let's recall that for every face record, we store the inner components. So we have the half edges that are in the inside, for the holes, and then we have the outer components. Now for the pentagon, the outer side, the outer face has an inner, that's the pentagon, but then has no outside. Also the hole has an outer component, but has no inner component. So the inner components can be nil. So we just have to point to the edge list if there is an inner component, if there is an outer component. Okay, now two observations. The enclosing face is always to the left if we walk around this. The pentagon here is enclosed by these counter clockwise, and the pentagon is always to the left of it. So how do we know when we walk at the outer or inner boundary? We can observe the angle. So if we have angles that are larger than pi over 2, so if we walk here clockwise, then actually we walk on the inner boundary. If the angles are less than 90, less than pi, then we walk on the outer boundary if we make a left turn. So this is how we know if we are in a face, if we are actually in the hole. So if we here, if we would walk around the triangle in clockwise, then all the angles would actually be larger. So this is the inner boundary of this pentagon here. So this is when the angles are larger than pi. If the angles are less than pi, then we walk on the outer boundary of this pentagon. Okay, so let's start to observe, make more observations here. So there is a graph that will define the cycles enclosing a face. So for every face, we can kind of have the convention that the leftmost vertex is kind of the start of every cycle. So that's how the faces here are labeled. So vertex 1 is the first face. So then we have the faces 2, 3, 4, 5, 6, and 7. So that's one way to identify the faces. So if we look at the first face, so it's an outer boundary for 2, that's phase 2, and if we are visiting vertex 6, also faces 3, so it is not, I mean, the thing that is outside here is 7. So actually all the faces are actually in inner, so the cycle here visits actually all the faces except the 7th one. So this is when we would go counterclockwise, we would actually encounter all the faces. And actually, I'm sorry, clockwise. If you visit counterclockwise, so counterclockwise is going this way. So we're going to 1, we will visit 5, 3, 4, 2, and 6. Okay. So the order here is actually, as I realize now, the order for the x-coordinates. Yeah, and the visiting here, so this is the clockwise. So the counterclockwise visit will indeed visit, will visit from 1, you will go to 6, then you go to 2, 4, 3, 5, and then back. Okay, cycles. and faces. So we have these cycles, we have inner cycles and outer cycles. So for every face we denote a cycle for its inner boundary and its outer boundary. So here you see the cycles. So for this example, so we have the components, the inner. So the inner for 7 is all alone. The outer for 7, so the outer for 7 is also the inner is connected to the inner for 3. And the inner for 3 here is somehow connected to the outer cycle for phase 6. So we have the outer cycles for 0 and 2. They are linked to the inner cycle for 1. So for each connected component in the graph, so if we look at these boundary corresponds exactly to all the set of cycles incident to one face. All right, then we can detail the algorithm, so we can update the face records now. So the updating, so the last statements in the map overlay algorithm can be replaced by 4 next statements. So we make a graph with the boundary cycles. So the nodes corresponds to the boundary cycles, and the edges that are connecting each whole cycle to the left of its highest leftmost vertex. So in a way, the slides should have been read next to each other. So perhaps if I should backtrack a little bit. So the statement that is here is actually saying how this graph was made, the graph of the connected components. So we actually are looking to the leftmost vertex. So this is why for this inner cycle, we actually are looking at, so from the outer cycles, we're looking to the left, and there's only one vertex there. So that is an important observation that I kind of missed. I'm trying to explain how this graph was built. Okay, so we compute the connected components, and for every connected component, we can make the face record for each face that is bounded by the cycles. So now comes then exercise 3. So we have one running example for this lecture, the pentagon overlaid with the triangle. So for that example, construct all the face records and illustrate how the graph is being used. All right. So let me now come to the cost analysis. So here is essentially the main theorem. So I'm running rather fast on this. The map overlay of 2 subdivisions. So we have the input, which is the number of vertices now. And we have the complexity of the overlay. So the complexity of the overlay will be determined by the number of edges and the number of faces. So we have this n plus k factor. It is an output sensitive algorithm. The cost for an output sensitive algorithm contains the size of the input, which is the little n, and the size of the output, which is the k. Now, in proving this theorem, there are two considerations to apply, so two results. So the main result of the previous lecture is that the algorithm to find all intersections of the line segments has a cost that is n plus I times the log of n. So the k actually includes this capital I. And then we have the computation in the map overlay. So these are the steps 4 and 5. And now I should back up a little bit. So in some sense, the steps 4 and 5 are defined here. And this term is determined by the degree of every vertex. So we have a new intersection point. So the degree of that vertex is the number of edges that are incident to the vertex, and that is going to determine the costs. Now the connection of these steps, so these are essentially all primitives. So in some sense I got confused in explaining this. For the main result, what actually mainly matters is that these connections can be done in a constant time. So these are steps 4 and 5 in the cost analysis, and this is proportional to the degree of the vertices. Okay, I will end by outlining the operations that we now can do. So we understand the subdivision overlay problem, and we can apply this to any two polygons and compute their union, their intersection, and their difference. So that can be solved by this data structure of the doubly connected edge lists. With the union, consider the outside, the outer face, and you run there along. That's what you keep. For the intersection, we have a hole, and for the difference, you can see that you have to run around the piece that is the intersection of the two. So we can have this Boolean algebra of working with polygons. All right, and what is important here is that the operations, they all can be done in n plus k times log n, where the n is the size of the input and k is the complexity of the output. Okay, in some sense, I hope that this lecture was not too confusing. So we are closing off the second chapter in the textbook. What is important is that the lecture should prepare you to read the textbook. So it's also important that in kind of absorbing the material in this lecture, the slides were kind of terse and perhaps a little bit too short. You should solve the exercises. I think you can solve the exercises with the information that is on the slides, but please also read the textbook. So there is no Jupyter notebook corresponding to this lecture, not yet. But building up towards the first computer project, it would be good to explore the Python interface to Seagull, and in particular how you can access the things that are exported in the kernel. So we have seen what that the point is exported to the Python programmer. There's also a segment data structure. How do you work with these edge data structures as a Python programmer? Explore and find this out. So also browse through the documentation of the Seagull. So that gives you another way to get access to the material. So compared to the previous two lectures and also to compare to the next lecture that follows, this is a little bit a shorter lecture, but more as an application of the line segment intersection problem. So the previous lecture was quite detailed and thorough. That is central in this chapter here. In the next lecture, we start the third chapter, starting with the art gallery theorem, the Watchman problem, and mainly talking about the complexity of a triangulation. So that will be then important for the subsequent lectures in that third chapter.